Hello everyone and welcome back to another video here on the Hidden Quantum Champions. Today we are looking at a company called Paragraf. They are making graphene-based sensors accessible to the world of quantum, so they are using them for cryostat applications. And if you are interested in learning more about these mass-produced graphene sensors and how they can actually be used within your quantum technology stack, then stay tuned for today's video as we are diving deeper into Paragraf. And with that, as per usual, here we are on their website. So you can see Paragraf. There's also a link to a store, which of course we're going to check out in a bit. Then we have here already the key application, right? So it says quantum computing, Paragraf, cryogenic sensors are providing a solution to detect and characterize magnetic fields causing decoherence in quantum processors. Maybe a quick step back on that. So why do you actually need to be able to measure these magnetic fields? Think about your superconducting qubits that are sitting in a cryostat. Superconductors are, by definition, let's say, expelling the magnetic field. So the magnetic field is being let's say, focused outside the superconducting regions. And if you have now a junction, for example, like a Josephson junction that you actually need to build these superconducting qubits, then in this junction you don't have superconducting material. So it is, well, a region where the magnetic flux would go. And that means if you have some magnetic fields within your cryostat, then there's a likelihood that these will go into your junctions and hence change the magnetic properties of those junctions or change the electric properties of those junctions, right? Because if you have a magnetic field in there, you have some circulating currents that it induces, and hence you change the properties of your magnetic field. So that's why usually you want to avoid these. When you're cooling down the system, these fluxes, they are kind of randomly distributing, and you're usually putting some flux traps on your chip as an example to avoid the magnetic field to go into these junctions and hence altering the electric properties of your system. So that's why knowing these magnetic fields and characterizing them is very important. And you need sensors that are very, very, let's say, sensitive, because these magnetic fields can be very small. They also need to be very fast because these magnetic fields can also rearrange. And I guess that's what we are going to learn about. And then probably also about the unique technology that they are using here to build these sensors. So magnetic field sensors for quantum computers, 3-axis cryogenic Hall sensors. So our millikelvin rated 3-axis probe is the first and only Hall effect sensor capable of measuring magnetic fields from room temperature all the way to temperature extremes down to 10 millikelvin. For the first time ever, this enables users to measure magnetic fields in real time in X, Y, Z orientation with microwatt power dissipation and down to the microtesla resolution, opening the door to in situ sensing of unwanted noise in the dilution fridge during operation and across warm and cool down cycles. So there's a couple of things in here, right? Real time, I think I mentioned that already. We see the sensor type is a Hall sensor. So how does that work? Basically, you are looking at something we call a Hall bar. So you're taking a structure that looks like a bar, and on the long ends you apply a current. And now if a magnetic field is moving perpendicular through this bar, then you will see nothing in the current, but actually what will happen is you will have some redistribution of the current because the magnetic field is kind of moving, tilting the current towards one side. You have these circular motions, right? So if you had, for example, the current coming from the left side going to the right side, or for you have to do a different way around, so left side to right side, and now you have a magnetic field, it will basically, instead of moving horizontal, it will either go down or it will go up due to the circular motion, and that actually produces a voltage drop across the upper and the lower side of this bar. So that's what is called the Hall effect. And if you have some, let's say, little Hall bar inside your system, you can basically with this measure the magnetic field that is running through the system by measuring the voltage drop between the upper and the lower side of this bar structure. Now, that said, you can do this very nicely with graphene because it has very good electric properties. It conducts very well. It has very less impurities, and for that you have a very pure current flow, and that actually helps to measure these effects. Hall effect sensors have been around ever since. They are in your smartphone already today, probably also in your computer. They can be manufactured in semiconductor materials at high scale. But not with graphene, because graphene is something that as of today is still hard to manufacture on an industrial scale. Now, quick zoom out on graphene. So graphene is a monolayer material. So you have carbon atoms like in your writing pen, like in a diamond, but they are ordered in a, let's say, a layered fashion. So you have XY planes that are connected in hexagonal shapes of these carbon atoms, and then these planes, they are stacked on top of each other, and they are basically bound to each other with the so-called van der Waals bonding, which is very loose. That's also why you can use it very well for pens to write, like the graphite pens. Graphite is basically just a lot of stacks of these graphene layers, and when you're writing, you are basically spreading these layers on the piece of paper, and that's why it actually it rubs off so well, because the van der Waals bond is very weak. And now the idea to make graphene is actually quite funny. It came up, I think, during some, let's say, physics tea kind of session. I mean, if you know more about the details, let me know down in the comments below. But as to my knowledge, I think it was like a physics kind of tea session setup, and people were having tea and thinking about funny ideas to try out. And somebody had the idea to basically create this two-dimensional material. And up to that point, it was not clear if two-dimensional materials can even exist by themselves, if it's stable or if it's just crumbling up if you're trying to produce it. And they took a pencil and they wrote on a piece of paper. So they rubbed it off on a piece of paper. Then they took Scotch tape, put it on top, exfoliated some of this, let's say, pencil material of this graphite. And then they just took Scotch tape and put it on the Scotch tape. And they basically exfoliated, did it a couple of times, and then transferred some of that on a substrate, and then looked at it under the microscope. And indeed, they managed to find some graphene on there. So they found the first time in human history a true two-dimensional material, which then also led to a Nobel Prize, and so on and so forth. So graphene itself is a super interesting material, not only because it's two-dimensional, but also because you can study very interesting quantum effects on it. The Hall effect works very well, and that's why it's very well suited for these cryogenic applications. Now, the Scotch tape method has for a long time been the only way to actually create a very high quality graphene. There were also other ways, ideas of how to grow it in a crystal growth environment. However, the quality of that material, of that graphene that has been grown in this crystal growth machines, has not been as high as the exfoliated one. And that's because you are introducing impurities. The graphene is not true graphene. There might be missing spots, or let's say overlapping areas, so that you at the end up with something that is more like a high quality graphite with a lot of impurities in it, but not actually a graphene. I'm not an expert on that, but just to say, so for a long time, that was the only way to actually produce these graphene layers by using the Scotch tape method. And even when I was still in my physics studies, there was a clean room which I would walk by every once in a while. And there were always students sitting in there, usually would ask the bachelor students to do that, that were exfoliating graphene and looking under the microscope and searching for the single flakes. Of course, that later on was automated and so on, but just to say, so this is something which for a long time in the scientific domain had still been applied. And I think nowadays there are very sophisticated ways to actually stack this also with hexaboron layers and so on, and also to twist these graphene layers against each other, so stack two on top of each other and twist them. But that's something for another video I don't want to talk about today. Okay, back to the text. So there's X, Y, and Z orientations. That's of course clear, right? You're measuring the magnetic field in all three different directions. Then you have microwatt power dissipation. It's also very important because within the cryostat at the low cooling stage, so in the 10 millikelvin, you also only have in the microwatts of cooling power that you can create down there. So if you have something that let's say consumes milliwatt of energy, then you will heat up the system locally, which you don't want with your quantum chip. And you can go down to the micro Tesla resolution. Now, a Tesla is a very, let's say, strong magnetic field. So if you have a 1 Tesla magnetic field, this is already pretty strong. Usually you are in the single Tesla regime when it comes to, let's say, superconducting magnets. Also, for example, in your NMR scanner in the hospital, it's usually in the Tesla regime. When you're looking into, let's say, the more day-to-day magnetic fields, you are more in the millitesla range. But micro Tesla is already pretty sensitive. So this is even 1 order of magnitude below, right? So that's very interesting. And I mean, you can, as I mentioned before, these fluxes in the magnetic field fluxes that you try to trap with the flux traps on your chip, they're happening between the warm up and the cool down. So when you're starting from warm temperature and you're cooling down, you're trapping these magnetic fields as the superconductor becomes superconductive, because at room temperature it's not, right? And that's why it's important to have these sensors that can basically run from room temperature all the way to cryogenic stage, because then you can really follow what is happening in your magnetic fields. So that's also an interesting property here. Now, improving error mitigation with Paragraf 3-axis probes. So the quantum computing industry is moving from research to commercialization. Efficiency and uptime is becoming crucial, and the exponential increase in qubits means finer control of source of noise is required. Paragraf's 3-axis probe is able to provide real-time measurements of magnetic fields down to the micro-Tesla resolution virtually anywhere in the environment. This enables quantum engineers and scientists to fully characterize their systems, reducing the impact of magnetic fields on their processors and enabling more useful work to be done. Learn how Paragraf's 3x probe and cryogenic sensors are uniquely suited to help solve issues with decoherence in quantum computing. And then there's a blog article linked here as well. So yeah, I mean, error mitigation is an important thing, right? Especially in this so-called NISQ era, so noisy intermediate state quantum computers, where you don't have the so-called error correction algorithms running on your chips, because they are pretty resource hungry. You need a lot of qubits to create one so-called logic qubit that is fully error corrected. You will still for quite a while run on the physical qubit, so you need to be able to suppress the errors as low as possible, as due to the fact that you're applying gates on gates on gates, you're accumulating errors, and at the end you don't want to end up with a random result, so you need to keep this error rate as low as possible. And this can be, for example, done by this error mitigation schemes, and yeah, that's basically what this idea is about, right? So you want to use this knowledge about the magnetic fields to actually be able to compensate, to mitigate those errors, right? Then you find some further news articles linked in here, a way to reach out to them, and as per usual down here the typical company information. The company is registered in England and Wales and based I think here in the United Kingdom. So let's quickly check out the products, right? So we've talked a little bit about it already. So there are different ones here: Hall sensors, molecular sensors, and foundry services. Let's quickly take a look at the Hall sensors just to get a bit of an understanding. So improving cryogenic systems with graphene sensors. Our graphene-based magnetic field sensors are the first and only Hall effect sensors capable of measuring high magnetic fields at cryogenic temperatures. Particle accelerators, fusion reactors, and MRI systems are all benefiting from them today. Why use graphene? Ultra low temperature operation down to the 10 millikelvin, exceptional stability up to 30 Tesla, so very high magnetic fields, right? And then superior accuracy with micro Tesla sensitivity. And here you see the different products. So there's a high field sensor, a general sensor, and a low field sensor, which all of them have some specific temperature ranges. The high one can go up to 30 Tesla. The low one can only go up to 0.5 Tesla. And here you also see the sensitivities of these products. Now, why do they have these different ranges? It probably also has to do something with the size of your hall bar, right? If you're making it bigger, you can probably measure, let's say, finer magnetic fields because you have a larger, let's say, area for the electrons to actually do this circular motion. If you make it smaller, then, well, you're reducing the range of motion for the electrons, so you need a stronger magnetic field to actually tilt them up or make it shorter maybe as well. I don't know. And that's, I guess, where these different sizes of the where the different sizes of the sensors probably create these different environments. But again, I'm not, let's say, an expert on quantum Hall sensor design. There's something here about quantum computing again, then magnet calibration, which I guess plays a big role also in this MRI scanners, for example. And then, yeah, there's further information down there. Now let's quickly also check out the other sensors. So there's the molecular sensor, graphene molecular sensor, GMS, the PMF2000 GFET, which I guess is graphene FET, so field effect transistor, is Paragraf's next generation graphene field effect transistor. Yeah, that's also explained. Succeeding the PV01 platform. Manufactured using Paragraf's proprietary direct growth process, it features polymer-free graphene channels for high consistency and reproducibility. Okay, so designed for sensing and research applications, the device includes 3 independent graphene channels arranged around an in-plane gate electrode for homogeneous field electric field. An epoxy encapsulation layer enables reliable liquid handling and channel-specific functionalization, supporting multiplex sensing and internal referencing. Compatible with standard data acquisition systems, the PMF2000 is ideal for advanced GFET sensor development. Accessories including the plug-in graphene breakout board and GFET discovery kit, enabling simple and rapid proof of concept and design prototyping. And I mean, here you see the sensor. I guess that's the sensing area here, and then you can play around with it and try these different where was it explained here homogeneous electric field experiments with this system, also with liquids, right? Okay, then I guess that's about this one. And then they also offer foundry services. I guess that goes to the, let's say, to their proprietary graphene growth process. So Paragraf is redefining graphene deposition and device processing. We do not use metal catalysts because copper in the past was a typical catalyst that people would use, which is not CMOS qualified. So you cannot use it within a CMOS clean or process it within a CMOS clean room, which is where most of the, let's say, standard industrial, but then also the small scale device clean rooms are based on CMOS. So basically you could not combine these two, resulting in superior quality and performance without the contamination and variance caused by other techniques. We are able to synthesize graphene directly on wafer using industry standard techniques, ensuring compatibility with our processes and platform. Paragraf works with customers to bring the wide range of product to market, including magnetic field sensors, ion sensors, and graphene radio frequency electronics. Our vision is to further develop 2D material solutions to underpin future computing. We welcome contact from partners who are interested in working with us and or investing in accelerating progress in these areas. Please contact, and then there's the contact form below here. Okay, so I guess that's it about the products and the services that they're offering. You can also get them here in the store, right? So you can, I guess, buy directly from them the different sensor products, and they are, as far as I see here, also directly available. So you can just add it to your cart and then order it from them right away. So it is a product, right? Let's quickly also learn a little bit about the company, and then as per usual we wrap it up. So our story: Paragraf is the first company in the world to mass produce graphene-based electronic devices using standard semiconductor processes. Our graphene Hall sensors GHS and graphene field effect transistor GFET, currently in production, and other semiconductor devices in development, make use of our proprietary graphene growth process to fully harness the wonder materials mirrored features. Our products deliver superior sensitivity, robustness, and energy efficiency to solve important problems in a range of applications, including automotive, industrial automation, cryogenics, healthcare, and agri-tech. At Paragraf, we are committed to materially impacting critical global challenges by driving a 2D materials revolution in the semiconductor industry, which we believe will facilitate massive improvements in the performance of technologies across all aspects of life. As spin-off from the University of Cambridge in 2018, Paragraf has raised $140 million over 3 rounds of fundraising and is widely recognized as an emerging tech leader. Then you see the executive team here, as well as some other information. Here about the funding history of the company. So founded in 2017 here, and then you can see as we are moving over here. So partnership with CERN. 2021 announces new graphene Hall effect sensor. So that's kind of the sensor that we've been looking at. Then there's an acquisition here. So Cardia Bioacquisition accelerating growth in the biosensors market. Then we see the GFET product, which has been launched. That's the one that we just saw right before. 2025 Innovate UK grant and partnership with Anchor Materials and TechMed. Okay, so I guess that's it for today. I hope you liked the video. For sure, I think this is again one of these hidden quantum champions companies that already have a product that is already selling, that is already in the market. People are using it. So I think it's like one of the cases where we see that quantum technology, as in creating single layer materials of atoms, is being, let's say, employed in today's electronics world, not as in we are just taking graphene and blending it into your, bicycle material to make it stronger, or your tennis rack and make it stronger, but really to create electronic sensors with properties or electronic devices with properties that have not been there before. So from my point of view, very exciting, and it seems like they have cracked the nut to actually process this on a industrial scale, which enables, of course, to make it cheaper, to make it more available, and maybe even to mass produce it at some point. Because right now I think it's still, let's say, small production batches. I guess they're not creating millions and millions of these sensors on a monthly basis. But again, I think there's a lot of room to develop here into, and we also see with these acquisitions that there are further markets that are being opened up for Paragraf. So from my point of view, one of these very interesting companies to keep on the track. And with that, as per usual, I hope you liked today's video. If so, please make sure to give it the thumbs up and subscribe if you don't want to miss out on the next one. I'm looking forward to see you there. Until then, bye-bye.